Back to solving the world's greatest puzzle. I'm going to try to be a little more clarifying. The marker. Okay, here we start. All right. Some supporting evidence in the first video, and it's hard to understand my words, so I'm going to try to talk a little bit clearer. Now, like I say, it's freestyle. I'm probably not right, but we'll attempt it anyways. Now, about the dark energy, the expansion force. That's the opposite. The expansion force is opposite the losing volume. We see matter losing volume. I mean, we see it readily. We see as we look into the center of galaxies, we suspect a body where the escape velocity becomes or exceeds that of the speed of light. So it gives it that black hole kind of mystical, magical, science breaks down kind of feel. And science should break down there. Of course, it all should make sense if your science is right. But anyways, we're losing volume, baryonic matter is losing volume as the field is expanding, of course. Now, you can see this difference. That's the difference in the volume of a nucleus. Nucleus goes to its electron shell and be the most readily available description. But the field is the electromagnetic conduit spectrum that light traverses through, and it appears like a particle sometimes because, well, the particles we use to measure it, we use particles to, I mean, half the world particles, so anytime a particle becomes in front of another particle, well, the field shifts, changes, appears like a particle and shifts, you know, all that good stuff. Everything is connected together, but electron, cloud, and baryonic matter, nucleus, the size difference, big time. Well, we actually got an example of this, and what we can call this expansion, we got an example of it. We've actually made a muon, which is a heavy electron, so to speak, same charge, supposedly, the way we measure everything, of course, and the way our instruments, in our tests, I mean, it all plays a part of what our results are, of course, but what happens when we introduce a muon to an atom? Say we take one of these electrons out and boom, throw in a muon. Well, that muon is a good example of the force rising, the dark energy force rising. And what happens happens there? Well, the nucleus shrinks. The nucleus actually loses volume, loses volume, loses volume when a neon. Mhm. 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 Neon. Mhm. Neon. A heavy electron. Let's see. Mhm. Electron is introduced. Okay. That's an example of the actions at play here. Now, so this strong force, I mean, boy, that's a head scratcher. Two protons in the same spot must take a heck of a force compared to, say, gravity. Should be the weakest force. But with gravity, you look around, I mean, the whole shape of the universe is pretty much the result of it. Huh? I imagine at the beginning, electromagnetic static charges that kind of took play in the shape, and then gravity takes over. And, well, when a star would be, let's say, fusing, then that's heat would be generated, but then when the heat stopped, and gravity would collapse it pretty quick. But as far as the heavier elements being created there, no, I don't know about all that. Perhaps, maybe, maybe not. But anyways, now this theory, this model rather, electromagnetic pulse engine, man, it would have to work, wouldn't it? I mean, being that the opposite. I mean, all your antimatter. We can generate an enormous amount. Say we take this electron cloud and we shrink it down to the same size as that nucleus. It's going to appear as antimatter. But have you ever heard that I can't see the forest for the trees? We can't see the antimatter for the light. You know, at the beginning, energy. Energy is consequence. But energy, the only way that energy is possible is when an opposite, let's say an entity and its opposite, react with one another. So without an antiparticle, without its antiparticle, which in this case is totally different than what we think, you can't have energy. So, so when a positive one can only have energy when its exact opposite is interacting. So it's got to interact. This must interact with this to create energy. So the light that I'm seeing this with is the opposite of the what's hidden way inside those electron clouds that are shape and everything, and so on and so on. So energy, the conservation of energy is hogwash because obviously if we started from zero, there's less energy. So it's going to be created in what we got now. I mean, you gotta get rid of the hogwash. So energy, the potential energy now perhaps is a consistent thing throughout the stages acting with its antiparticle. But in this case, it's funny here because we look at, if they were combined, it would annihilate rather. Now, E equals mc squared is a very useful equation used all the time. But here's the tricky part, not the tricky part. Now, I don't have this exactly right, but what it's gonna be is this weight. If we measure the mass of this, we pretty much can know the equivalent of it by using the speed of light squared as a volume of the field surrounding it. So in order for this to equal, in order for the electron cloud to equal the nucleus, the positive, in order for the negative to equal the positive, it would take roughly a volume that corresponds with the speed of light squared. So this times the speed of light squared. If you took that volume, now that we're adding a second and a speed, whatever we measure light is 186,000 miles per second, and that's all a concern and stuff. But it's just, it all works out. Now, if we take that amount of this, so that's going to be equal in energy as far as we see it, because it's equal with that. It's the exact opposite, and that's the energy equivalent. Now, we know energy by this field. I mean, that's something we can sense. It's something we like. Everything we touch, I mean, it's all exchanges of electrons. And these electrons are just flowing from one thing to another because everything's like positive ion, of course, because the field stretches so big and far, billions of light years, while the positive baryonic matter is condensed and rigid. So would an annihilate go? No, that does not annihilate. The energy, let's see. The energy it puts off is just spread out. Now where does the nucleus go? Let's see, if we're measuring energy from the sun, fusion, I'm gonna let this, I'm gonna think about this a little more before I say something totally stupid. I mean, amongst all the other stuff, I say stupid, but let's see electromagnetic pulse engine. Of course, it's gonna work because of the opposites. I mean, if you shoot out microwaves and a jet engine kind of thing, it should propel. This, just like dark energy, actually is causing gravity. So, and what else? Everything makes sense. I mean, it just, everything comes together. All the sciences make sense. The small, the large, it all works together. Let's see, so much supporting evidence. Thousands of paradoxes just seem to clear up, but coming through them all at once is kind of hard to do. But okay, let's see what else. What else? What else? Well, here we're on. This is our focus. 56 is balance, electromagnetic balance, electromagnetic balance, electromagnetic balance. So it's an exact balance with the electromagnetic spectrum being that this can be permanently magnetized. This and this. Now, I'm believing iron is 56. I'm not totally sure about that. I should look these things up so I'm too retarded. But I'm trying to be right here in the middle and trust in all these specialized, working in their own field. I'm gonna try to trust all their work, all their math, and just assume that's true from what makes sense to me. But I gotta stay right here. I can't go down too far, or I lose track of all of this, and can't do that. So I try to stay in the middle, and, look around, make sure everything's gonna combine right up in the middle, and not be too eccentric. Which knowing this stuff or trying to understand this stuff might make most people seem kind of off anyway. I wouldn't have it any other way. I love it. This is God's language. Science, by the way, will never prove or disprove God. It's impossible. It's impossible. So what we're doing next is, that's the balance. So we're in balance with the magnetic spectrum, and we're in balance also with the strong force. It's holding everything together. And the weak force. This is the middle. And weak force. Okay. Pretty much. So, great place to start. Great place to start. So, the balance there. So, this is all balance. So, everything's balanced. So everything's in balance right here. Strong force and weak force, the electromagnetic spectrum. Iron is we're the universe, the stage that we're in our locality as we speak. So when we look at an object, say, we look at an object, a particle, for example, a particle, it doesn't move. So then we look away, and then we look back, and the particle is moved. It's obviously in the way we're measuring it. What are we doing? We're using light waves, electromagnetic spectrum, to view it. Well, that's what's stopping it. That's what's blocking it. That's like dark energy having the same amount in each direction would cause an object to stay still. Well, that's what we're pretty much doing when we do that, causing it to stay still by locking it in. Now we're using that same way an electromagnetic pulse engine might propel matter, which defies Newton's law of motion, by the way, but you don't defy nature. China made one, we made one. I mean, there's a chance that we're doing something wrong in the way we're testing or something that makes it look like it's working when it really isn't. I mean, that's always a possibility, but China showed to be working and ours did too. So, also, let's see what else. Oh yeah, there's all kinds. I mean, just thousands of things that come together. Works just excellent. Everything is something. I mean, if space was nothing, would we have a speed limit? If space was nothing, would gravity bend light? Heck, when we measured on an eclipse not too long back, 20, 30 years ago, but came up exactly like Einstein said, so many parsecs, however you pronounce that, when we measured a starlight far beyond our own sun, which was usually invisible to us because of sunlight, but since it was blocked by the moon, we could see that starlight, and it was bent just exactly like they said, sort of like a trampoline with a volleyball, with a bowling ball in the middle. It's kind of like space. So, time. Is time actually relative? Well, it's more like the muon, how it ups the force of the dark energy that kind of shrinks, which is opposite of the volume loss in the nucleuses. Well, space has a magnitude. Now, say that our nucleuses are very rigid. Well, space goes from less rigid to way less rigid. Okay, but there is magnitudes of it, of course. And well, so we actually can travel through a bit of space. Let's say a pendulum swings through a place where it's more rigid than another place. It actually traversed, although the distance seemed the same from an observer, it traveled through more of its opposite, more of its negative field. So distance is kind of like time, it's kind of relative. Not so much time, time is a rate of motion and distance at a certain speed. So what we have here more is a relative distance. It's more accurate than time being relative. Regardless, the math is excellent, theory is excellent. How many hours I sit there thinking, what the heck is he thinking to come up with time being relative? What is he putting? What kind of, like, is it on a treadmill or, I mean, what is space? I mean, this amazes me. How he come up with it, I'll never know. But thank God he did, because without that giant, I couldn't stand on his shoulders and see anything. I mean, without Einstein. So we always wanted to come up with quantum gravity. When actually, we should have been coming up with relative everything. So the rate of action, how far this thing goes through the field, and how dense, I mean, how much charge there is per volume of the field determines the relativity of time equations and in general and special uh, theories of relativity. Thank you. Einstein's probably one of my favorites. One of his favorite physicists, I believe, was Wolfgang Pauli, which anytime he was around, experiments, well, they turned out different than what everybody expected, which to me is awesome, because you just learn something. I mean, you just added way more knowledge to your set of understandings. Wolfgang Pauli, really good physicist. But let's see, what else do we have? No, just stuff. I'll make another video and another.